This video will affect changes that can be made to a system in equilibrium, and it will also address the effects on that system as it is adjusted back to a new equilibrium. And that principle, again, is called the Chatelier's principle. You have this sheet in your packet, so make sure you find it. I'm going to go through each one of these, but first, let's just remember what endothermic means. Endothermic means that energy has to be added. So for this reaction to take place, we're going to represent heat on the reactant side. The heat itself would be, quote, added to the reaction vessel, but we represent it on the reactant side. So by showing heat on the reactant side, we've now checked the box that we're showing an endothermic reaction. The next thing I want to point out is what the question's asking. The question's asking what's going to happen to the number of moles of hydrogen. So hydrogen is one of our products. Will the moles of hydrogen increase? Will the moles of hydrogen decrease? Will the moles of hydrogen stay the same when each of these changes is made to this system at equilibrium? So just to remind you, this is an equilibrium expression. At a certain temperature, this KEQ will equal a certain number. We don't have any actual values given to us, but it'll equal a certain number. As any of these shifts occur, let's just look at the first one. If we're taking some carbon monoxide away, that means that we're going to decrease the amount of carbon dioxide that we have. That means that the concentration will be lowered. Immediately, it's going to get kicked out of equilibrium because if these guys don't change right away, but this does, you're not going to get this same number. So that's when we get into Q territory, okay? So once it's kicked out of equilibrium, we can still see what this ratio is. It just won't necessarily be at equilibrium anymore. So to alleviate this stress or this change to the system, the reaction will shift, and therefore the concentrations in the other three will also change to kind of adjust. Remember that unless we change the temperature, this number stays the same. So that's why there are infinite numbers that can go in here, an infinite number of possibilities to keep this ratio the same, even though the actual values in here are changing. The overall ratio will still be the same as long as the temperature doesn't change and equal that equilibrium constant. Letter A says carbon monoxide is removed. In this case, carbon monoxide is a product, so we're decreasing its concentration. We're taking some out. The reaction will respond by shifting in order to replenish it. It may never get back to its initial concentration, but that's okay. Still, the reaction will shift. So the reaction will shift in this direction. That means toward the products. So while this reaction is kicked out of equilibrium, temporarily the forward reaction will speed up. And because that is true, the question says what happens to our moles of H2 gas, and the moles of H2 gas will increase by removing a product. Now we're talking about letter B, water vapor is removed. So again, we're removing a substance, but this time the substance that we're removing is a reactant. So if we take away some of the water vapor, the reaction is going to try to replenish it, and that means it'll have to shift toward the reactants. So the reverse reaction will speed up temporarily. And again, what happens to our moles of H2? The moles of H2 now are going to decrease because the reaction is shifting away from the products. One quick thing. Water here is a gas. If water would have been a liquid, because solids and liquids do not show up in a equilibrium expression, we just would have said no change. If liquid was removed or added, we'd just say no change. Here we are we're pouring in some more of, in this case, it's a reactant. So in order to try to get rid of it, right, do the opposite of what just happened, the reaction is going to shift toward the products, and that means we're going to get more moles, or our moles of H2 will increase. Again, we're adding something, but this time we're adding a product. So since we're adding a product, the reaction will shift toward the reactants to try to decrease the amount of product we just added. In doing so, it will also decrease the number of moles of H2 because that's also a product. Also, E, and I believe it's the letter G, those will be done at the end. So I'm going to skip ahead to F right now. Okay, this one takes a little more thought. So if you have gases, and we do, they're going to be affected obviously by pressure increases and decreases. So the pressure is decreased in a system by opening a valve to a second reaction vessel. So think something like this. Everything was contained, the whole reaction was contained over here. Now we open this valve and now it can spread out. So the volume has gone up. And that's not the volume of a specific species, it's the volume of the whole reaction of the system, right? An increase in volume means a decrease in pressure because they have an inverse relationship. So if the pressure goes down due to this volume increase, what is going to happen, according to Le Chatelier's principle, is that we now need to increase the pressure. So how can we re-increase the pressure? How does pressure increase? And in order to do that, you have to consider the number of moles, not of everything, but of gas on the reactant side versus the number of moles of gas on the product side. So look at your balanced equation. We have 2 moles of gas on the reactant side, and then 3 plus 1 is 4 moles of gas on the product side. So how are we going to increase pressure? Pressure is going to vary directly with number of moles. So to increase pressure, the reaction will shift toward the greater number of moles. So in this case, the reaction would shift toward the products, and that means that your moles of H2 would increase. In this case, we had 2 different number of moles of gas on the reactant versus product side. Sometimes they'll be the same. So if this was 2 moles and this was 2 moles of gas, then we would just say no change to our concentration of H2 because the reaction won't be knocked out of equilibrium. So this is our first one where we're having a temperature change. Okay, and what we're doing is we're adding more heat. So because this is an endothermic reaction, which is why it's always important, I think, to represent heat either on the reactant side for endo or the product side for exo. Now you can almost just treat it as if you're like adding more of this reactant. So if you're adding more of the heat, in this case, the reaction will go toward the products, meaning you'll increase your number of moles of H2. Okay? Be careful. If you add heat to an exothermic reaction, it'll be the opposite. And then if you cooled this, if you removed heat here, then again, it would go in the opposite direction. Also remember, when you have temperature changes, it's not just a shift in equilibrium. KEQ also changes. That's only for temperature. For all the other changes, the equilibrium position will change, but the constant will stay the same. So besides saying that the KEQ changes, we can actually do a little bit more. So KEQ is just, I'm not going to write out the whole expression, but it's going to be concentrations of your products, raised to the powers of the coefficients, over concentrations of the reactants. Well, in this case, your products are increasing their concentrations, your reactants are decreasing their concentrations. Therefore, KEQ is actually going to increase. So without more numbers, we can't tell by how much. We can't tell the value of KEQ, but we can definitively say, in this case, KEQ increases. I saved E and G until the end because in both cases, you're going to have no change to the moles of H2, okay? Anytime you add a noble gas, it is inert. It doesn't react. Yes, it will increase the partial pressure, but it doesn't actually change the pressures of the reactants or the products themselves. Therefore, there's no effect on equilibrium. Okay, so just watch out for that. It's anytime you add a noble gas. The other difference is, the other one where you're not going to have a difference is if a catalyst is added. So what happens with a catalyst is it does speed up the reaction, but it speeds up the forward and the reverse reaction by the same amount. So it never actually kicks it out of equilibrium. So again, no effect anytime you see a catalyst is added to the equilibrium, and therefore there'd be no change in the number of moles of H2.